You know, we usually picture atoms as these super stable little building blocks, right? The foundation of everything. But what if some of them are, well, kind of jittery, constantly on the edge of just falling apart? That's what we're diving into today, the wild, powerful, and sometimes dangerous world of radioactivity.
Just think about that for a second. What if an atom's core was just so unstable, so packed with energy, that it had to, well, spit out pieces of itself just to calm down? That's it. That's the core idea behind the incredible phenomenon of radioactive decay, and we are going to break it all down.
Okay, so to get why some atoms are so shaky, we gotta look right into the atom's heart, the nucleus. This is where all the action happens. So let's do a quick roll call of the main players.
All right, first up is the atomic number, or Z for short. Super simple. It's just the number of protons. Think of it like an atom's ID card. It tells you what element it is. 6 protons? Bam, you're carbon. Got 92? Hello, uranium. It's really that straightforward.
And then we have the mass number, which we call A. This one is just the total number of protons and neutrons all bundled together. It's what gives the atom its heft, its weight. So remember, Z is who you are, A is how much you weigh.
Okay, now this is where things get really cool. You can have atoms of the very same element, so the same number of protons, right? But they can have different weights. How? Because they have a different number of neutrons. We call these isotopes. A perfect example is carbon. Most carbon is good old stable carbon-12. That's 6 protons, 6 neutrons. But then there's its isotope carbon-14. It's still got 6 protons, but it's lugging around 2 extra neutrons. And that extra baggage, it messes with the balance, making the whole nucleus unstable.
And that instability? That's the whole point. Radioactivity is literally what happens when one of those unstable nuclei just decides, nope, I've had enough, and spontaneously disintegrates to find a more stable state. And when it does that, it shoots out energy and particles. And that stuff it shoots out, that's what we call radiation.
So, when a nucleus goes through this decay, what's it actually spitting out? Well, it turns out there are 3 main types of radiation, kind of like the main characters in this atomic drama. Let's meet them. So we've got alpha, beta, and gamma. Now, you really got to know that each one is totally different from the others. Getting a handle on what makes them unique is the key to understanding this whole process.
All right, this table right here, this is basically the cheat sheet for everything we need to know. Let's walk through it. First up, their nature. An alpha particle, it's a beast. It's basically a helium nucleus, 2 protons and 2 neutrons. It's the heavyweight champ. Then you have the beta particle. Way simpler, it's just a speedy little electron. And gamma? Gamma's not even a particle. It's pure energy, a high-frequency wave, kind of like a superpowered X-ray. Now let's talk charge. Easy. Alpha has 2 protons, so it's got a positive charge. Beta's an electron, so of course it's negative. And gamma, being a wave, has no charge at all. It's neutral. Okay, this next part is super important. Ionizing and penetrating power. Just picture the alpha particle as a bowling ball. It's big, it's heavy, and it smashes into other atoms, knocking their electrons off like crazy. That's what we mean by high ionizing power. But because it's a bowling ball, it gets stopped really easily, right? So very low penetrating power. Now think of gamma as a ghost. It's just energy. It zips right through matter, barely interacting. So it has very low ionizing power, but its penetrating power is off the charts. And beta? Well, beta's kind of in the middle.
And wow, look at this. This really drives the point home. The big, tough alpha particle stopped by a single sheet of paper. That's it. But look at the gamma ray. It sails right through the paper, right through a person, and you need a thick slab of lead or concrete just to slow it down. The difference is just incredible. Okay, so here's a mind-blowing part. When a nucleus spits out radiation, it's not just letting off steam. It's often changing its own identity, literally turning into a completely different element. It's like modern-day alchemy. But it's not random. It follows a very specific set of rules. Let's check out the rule book.
So for alpha decay, when a nucleus kicks out an alpha particle, what is that again? Right, 2 protons and 2 neutrons. So the math is super simple. The total mass, the mass number A, drops by 4, and the identity, the atomic number Z, drops by 2. And since the number of protons changed, both, you've got a brand new element on your hands.
Now beta decay, this is wild. It's like a little magic trick happening inside the nucleus. Get this, a neutron suddenly decides to become a proton, just like that. Now to keep everything balanced, it has to get rid of a negative charge, so it shoots out an electron at high speed, and that's our beta particle. So think about it. The total number of particles, the mass number, stays the same. But we just gained a proton, so the atomic number actually goes up by 1. And once again, a new element is born.
So what's left? Gamma emission. And you know what? This is the easy one. All that's happening here is that the nucleus has a bit too much energy. It's all hyped up. To chill out, it just releases a burst of energy in the form of a gamma ray. That's it. No particles change. The mass number's the same, the atomic number's the same. It's the same element it was before, just, a lot less stressed out.
Okay, so that's the physics of it all. But why should you care? What's the point? Well, this isn't just theory. We've actually figured out how to use this incredible power in the real world for some pretty amazing stuff.
Yeah, we've put these radioisotopes, these unstable atoms, to work in some seriously life-changing ways. In medicine, for example, we can use gamma rays from cobalt-60 like a super-precise laser beam to zap cancer cells. For science, carbon-14 is like a time machine, letting us figure out how old ancient bones or artifacts are. And in industry, we use radiation to see through solid metal, finding tiny cracks in airplane parts. It's everywhere.
But of course, with great power comes, well, you know the rest. The very same radiation that can save a life can also be incredibly dangerous if we're not super careful.
So where does this harmful radiation come from? Well, there are a few sources. You've got fallout from nuclear accidents, the huge challenge of what to do with nuclear waste, and even a steady little trickle of radiation that's always coming at us from outer space. Figuring out how to manage all of this is a massive job for scientists and engineers.
And that's why safety is absolutely number one. I mean, we're talking thick lead containers for storage. People who work with this stuff wear special aprons and gloves lined with lead, and nuclear waste, it has to be handled so carefully, usually buried deep underground in special sites where it can stay safe for thousands of years. It's all about having a healthy respect for the power you're handling.
Whew, okay. We have covered a ton of ground, haven't we? From the very heart of the atom all the way out to how it changes our world. So let's wrap things up and maybe test what you remember. But before we get to a little quiz, I want to leave you with this one big thought. Radioactivity is this two-sided coin, right? It can be a healer, but also a destroyer. It can give us clean energy, but it can also be a terrible weapon. Figuring out how we, as a society, balance its incredible promise with its very real danger, that's got to be one of the most important conversations we can have.
Okay, you ready? Let's test your knowledge. Just 4 quick questions. Feel free to pause and think about them. Number 1. Which type of radiation has the most oomph, the highest ionizing power? Remember the bowling ball. Number 2. When a nucleus goes through beta decay, what happens to its mass number? Does it go up, down, or stay the same? Number 3. Can you name just one of the medical uses we talked about for radioisotopes? And finally, number 4. Which of the 3 radiations is neutral, no charge, and wouldn't even be bothered by a magnetic field? Hey, thanks so much for coming along on this trip into the atom's unstable heart. And remember, always keep asking questions.